In this video, we're going to go over graphs for simple harmonic motion. So we're going to start off with a position versus time graph. And we're going to think about an object oscillating on a spring. So let's say that we have a mass here, and there's a spring, and that object is oscillating back and forth. This is the equilibrium position. And so when I think about this, we can make a graph of the position versus time. We're going to graph one full period of oscillation. So this motion is going to be repeating. One period is the time for one full oscillation. So for it to go to the right, back to the beginning, to the left, back to the beginning. So we'll start here, and we're going to get a sine curve. I missed the 1/2 period there a little bit, but that's okay. And if we were to write the equation for this motion, we would have x equals the amplitude times the sine times omega times t. Now, you may sometimes see a plus something right here, and that just deals with the phase shift. We don't really see a whole lot of those in this class, so we're not going to worry about that right now, but you have learned about that phase shift in math class. Let's talk about what these different parts of the equation mean here. This is our position. The coefficient that's in front of the sine, and this could also be a cosine if we started at a maximum, that's going to be the amplitude, or the x max. So when we have this oscillation, this is going between the negative x max and the x max. And so the amplitude is it's just a special name for the maximum value there of the position. Then we take the sine. This curvy W thing is called an omega. That is a Greek symbol. And omega is angular frequency. So it's 2 pi times the frequency. And it'll tell you how many radians per second or oscillations per second we have. Not oscillations per second, radians per second. It's also equal to 2 pi over period, because period and frequency are inversely proportional to each other. Make sure when you're calculating this that you have your calculator in radians, and this is just going to be our time. So we should notice that our time value is going to cycle through, and it's going to cause repeats after every period of motion. Now let's think about our velocity versus time graph. So here's velocity versus time graph. And for this one, we can use the slope of the position versus time graph to get the velocity graph. So this is a positive slope, so we're going to start with a positive velocity. Here we have a 0 slope, so we're at 0 velocity. Here we have a negative slope, so we're at negative velocity. 0 slope again here, so 0 velocity, and then positive slope. So back to positive velocity. So our velocity curve is looking like this, and this is, do the best I can. I did a little bit better than on the last one. And if you know calculus, you should notice that this is a sine curve and this is a cosine curve. And so the derivative of sine is cosine, and we get the velocity by taking the derivative of the position. So now when we write this equation, we have velocity is equal to V max times the cosine of omega times t. Now our V max here, this is going between V max and negative V max. And that is, that's that value. It's just the amplitude of the wave. I forgot to mention up here that this right here is amplitude. You can also measure it from here, but you always measure from the equilibrium to the maximum displacement. All right, so let's talk about, I'm going to rewrite this equation. The V max here is equal to A times omega times cosine of omega t. So notice that these two don't have the same coefficient. We have A and then we multiply by omega. And if you know how to take the derivative of sine, you know that you're going to take the coefficient of the time and multiply the cosine by that coefficient to get the derivative. So this piece right here, this A times omega, is the V max. So V max is equal to A times omega. And that's equal to A times 2 pi times frequency, which is equal to A times 2 pi over period. And so you can use an equation of a velocity you can use a velocity equation to find things like frequency and amplitude if you know what the coefficient is in front of the cosine or sine. This could also be sine. Now let's think about acceleration. So when we find our acceleration, we do the slope of the velocity graph. So here we have a slope of 0, so we start with 0 acceleration. I guess I should label this graph. And then here our slope is negative, so we get a negative acceleration. Our slope is 0 again, so 0 acceleration. Here our slope is positive, and then back to 0. And so our acceleration graph is looking like this. That one looks really terrible, but we'll roll with it. So here's our negative A max, and then A max. And when we write our equation for the acceleration, we have acceleration is equal to, and we can see this is a negative sign because it starts at 0 and goes down first. So we have negative A max times the sine of omega t. And we can rewrite this. This E max is equal to A times omega squared. So you can see that this coefficient is A. We multiply by omega, we get A omega for velocity. Multiply by omega again, we get A omega squared for our negative sign. And if you know how to take a derivative, you know the derivative of cosine is negative sine. And then you know you multiply by the coefficient of the time. And then times sine of omega t. So we can see that our coefficient right here is A max, and that's equal to A times omega squared. So that's equal to A times 4 pi squared F squared, frequency squared, or A times 4 pi squared over T squared. One more thing I want to cover here before we end this is another equation for A max. So as this thing is oscillating back and forth, we know that the maximum force is equal to mass times maximum acceleration. And that is Newton's second law. I'm assuming this is the only force acting on it. We also know that the maximum force is equal to, if we use Hooke's law, K times the amount that the spring is stretched. And the most it's going to be stretched is the amplitude. So the maximum force is going to be K times the amplitude. So now I can set these two equal to each other. So I get mass times A max is equal to K times A. And then I can solve for A max, and I get A max is equal to K times the amplitude over the M. And this will give me the magnitude of the maximum acceleration. It's just a nice equation. There's the bell. It's a nice equation for solving for maximum acceleration, and you need to know how to get that from these two equations. All right, that's it.